Hello and welcome back to Target JEE Advanced sessions brought to you by BYJU'S. Today's is yet another mathematics session, and today we'll look at applications of derivatives yet and again. In the previous session, we had looked at application of derivatives part 1, wherein we looked at topics such as tangents and normals, derivative as a rate measurer, approximations, and some very interesting theorem based on applications of derivatives. Today, we look at the other two topics, monotonicity and extrema. For a very detailed analysis of this chapter from the JEE Main and Advanced examination point of view, please refer back to our previous video wherein a comprehensive analysis has already been carried out. In this video, I will analyze the chapter from these examination point of view just by keeping at extrema and monotonicity in mind, and then we will do a quick revision of these two concepts before going on to the all-important question solving. So, extrema and monotonicity, how many questions have they fetched in the past few years in both advanced and main examination? Well, when you talk about the advanced examination in 2013, 2015 and 2016, the questions which came needed concepts of extrema to be used when you were solving the question. In 2017, the question which came required you to understand the monotonicity in order to solve it. So, 4 out of the past 6 question papers in the advanced examination had questions from this topic. Makes this topic really important, isn't it? In the main examination, these topics are not that often tested, but of course in the board examination you always get questions from increasing, decreasing functions and extrema. So it's definitely worthwhile going through these topics in great detail. It's a lot of fun also to solve such questions, so you might as well brush up your concepts and get a very good understanding of these two concepts and solve a lot of questions from here. Let's quickly look at what monotonicity and extrema of functions actually mean. So what exactly does monotonicity deal with? Well, monotonicity is a very fancy word given for determining the increasing and decreasing nature of functions. Well, for any continuous function, if you look at the graph of those functions, they increase sometimes, they decrease sometimes, all such things keep happening. So throughout the domain of a function, the function tends to go up and down and up and down, and all these things happen. So monotonicity will help you determine where is a function increasing and where is a function decreasing. So how does monotonicity actually do this? Well, it does this through the help of derivatives. So what happens when a function is increasing? So when a function is increasing, it is moving upward. So if a function is moving upward, you can clearly see that at every point the tangent will have a slope which is greater than 0. When a curve is moving upward, the tangent will have slope greater than 0. Or in other words, if you differentiate this function in the region where a function is increasing, the derivative of that function in any of these points in the domain where the function is increasing will be positive. So for an increasing function, the derivative of that function in the domain where the function is increasing will be positive. Well, when a function is decreasing, it's going to be the other way around. So when a function starts decreasing, you will clearly see that the slope of this particular function, the slope of the tangent to this particular function will have a negative slope when the function is decreasing. So this means that as soon as the function starts decreasing, the derivative of the function at any point in this particular domain will have a negative value. So now, mathematically, what would an increasing function be? Well, not keeping derivatives in mind, if x1 is less than x2, then for an increasing function, f of x1 will also be less than f of x2, or maybe it is equal in some cases. But for a strictly increasing function, f of x1 will be less than f of x2. It's the opposite for a decreasing function. If x1 is less than x2, then f of x2 will actually be less than f of x1, or f of x1 will be greater than f of x2 for a strictly decreasing function. And in terms of derivative, f dash of x will be greater than 0 for a strictly increasing function, or greater than or equal to 0 for an increasing function in a domain a comma b, and for a decreasing function it will be less than or equal to 0. For a strictly decreasing function, it will be less than 0 in that particular domain. So monotonicity deals with increasing and decreasing functions, and we make use of the concept of derivatives to arrive at the regions where the function is increasing or decreasing. So the algorithm that people use to determine the domain where a function is increasing and the subdomain where a function is decreasing is very simple. Take a function, differentiate the function, and put the value of the derivative to be equal to 0. So if you have the function y equal to f of x, what you do is you take the derivative of y with respect to x, dy by dx, that will be equal to f dash of x, and then put this to be equal to 0 and find out the points where f dash of x equal to 0. The points where f dash of x equal to 0, these are the critical points where the function is going to change nature. Then you divide your domain. So let's say your critical points are all the ci's. So if your domain is a comma b, then divide your domain into a comma c1, c1 comma c2, so on up till cn comma b. And in all these subdomains, find a point and evaluate the value of the derivative. If the value of the derivative is negative, this means that the function is decreasing in that subdomain. If the value of the derivative is positive, then the function is increasing in that subdomain. So it's a very easy concept and a pretty important concept as well. So a natural extension of monotonicity is what is covered in the next concept, which is called as extrema. So we've seen that when a function changes its nature from increasing to decreasing or decreasing to increasing, what happens is there is a point where the slope of the tangent to the curve is actually equal to 0, and these points are called as our extreme points, because in that subdomain the function is going to attain a maximum value or a minimum value, and these things are called as local maxima and local minima, and the maximas and minimas are what are generally called as extremas in mathematics. So when you apply the algorithm of f dash of x equal to 0, you find out these critical points where the nature of the curve changes. But we still don't know what exactly is happening at those critical points, whether it is a local maxima or a local minima. And this is where the concept of extrema comes into picture, and we look at the second derivative, because now if the second derivative is positive, this means that we have hit a local minima, and if the second derivative is negative, this means that we have hit a local maxima. But sometimes it so happens that there are these critical points where the slope of the tangent to the curve is 0, and we get f double dash, the second derivative, also to be equal to 0. Such points are actually called as points of inflection, where actually the curve does not change nature from increasing to decreasing, but it just gives us a false sense of changing. So what happens is something like this. Look at the curve of x cube at x equal to 0. Well, till then the function was increasing at a different pace, and from x is equal to 0, it is increasing at a different rate, but it is still an increasing function throughout its domain. So at x is equal to 0, even if the slope of the tangent to the curve is 0, the curve is not changing nature. So these points are called as points of inflection. These are not extreme points. These are points of inflection. So extrema helps us to identify local maximas, local minimas, and points of inflection. Well, there are amazing applications of extrema. We can maximize functions, we can minimize functions, we can do all these things with extrema, and you'll actually be exposed to such questions in the next few minutes when we will actually solve a few questions. So monotonicity and extrema are really interesting concepts, very beautiful concepts, and really interesting questions can be formed out of these concepts, and we will look at some of these questions and have a lot of fun solving these questions. The first question that we're going to look at is a multiple correct answer kind of question. So here is the question. So in this question, we've been told that x log x plus x equal to lambda. So this has been given to us, and we have to check which of the 4 given options are correct. Now again, remember, these days in the advanced examination for multiple correct answer kind of questions, you have partial marks, so you can check some of the options and leave the others in case you are short of time. But of course, we will always try and attempt the question in entirety. So let's look at the first option. The first option says that this thing, x log x plus x equal to lambda, this equation has two solutions if lambda equal to 0. So if lambda equal to 0, what do we get? Let me call x log x plus x as f of x. So if lambda equal to 0, then I have f of x is equal to 0 as my equation. So f of x equal to 0. Let's try and solve it. X log x plus x equal to 0 implies x times log x plus 1 equal to 0, correct? Now this means that x equal to 0 or x equal to 1 upon e, correct? Because you will have log x is minus 1. If log x is minus 1, then x is e to the power minus 1, which is nothing but 1 upon e. It seems that if lambda equal to 0, we have two solutions for x equal to 0 and x equal to 1 by e. So this seems like the first option is a correct answer. But hang on, what happens if x equal to 0? If x equal to 0, you will have to plug in the value of x equal to 0 in the expression for f of x, which has a log of x. And log of 0 we know is not defined. So x equal to 0 is not at all in the domain of f of x. So if lambda equal to 0, x equal to 0 is not a solution. X equal to 1 by e is the only solution. This means that if lambda equal to 0, there is only one solution to the equation. So option 1 is straight away false. Now let's look at options 2 and 3 because these are very related options. Let's look at both these options together. So they've given a range of values for lambda. They've said that lambda belongs to 0, 1 by e square, or lambda belongs to negative 1 upon e square, 0. And then they say that there is exactly one solution, or there is at least one solution in these ranges for lambda. Let's see if any of those is true. So before that, we know that we cannot input the value of x equal to 0 in f of x because log of 0 is not defined. So is the case with all negative numbers. We cannot input x as a negative number in f of x because log of a negative number is not defined. So what happens to the function f of x as x approaches 0? And again, x is going to approach 0 from the right side and not from the left side because x cannot be a negative number. So as x approaches 0 from the right, we'll have to take the limit of f of x as x approaches 0 plus to find out what happens. So limit as x approaches 0 plus of f of x is nothing but limit as x approaches 0 plus of x log x plus x. Now evaluating the limit of the second term is very trivial because as x approaches 0, limit of x is also going to be equal to 0. But as x approaches 0, what happens to x log x? That's interesting because when x is almost 0, this x log x is going to be 0 times negative infinity. Now 0 times negative infinity, we can forget the negative for now. It's of the form 0 into infinity, and that's an indeterminate form. Now we need to use some way of evaluating this indeterminate form. Well, we know the L'Hopital's theorem, but L'Hopital's theorem can be used only for infinity by infinity form or 0 by 0 form. But also we know that every indeterminate form can be converted into are interconvertible. So from one form to another we can easily convert them. So I'm going to write a limit x tending to 0 plus of x log x as a limit x tending to 0 plus of log x divided by 1 by x. The second term I'm going to drop it because it's anyways going to be 0. So I'll drop the second term. I'll just keep this limit. This is what is going to be the value of the function as x approaches 0. Now this is of the form infinity by infinity. Well, to be very honest, it's of the form negative infinity over infinity, but that's okay. We can use the L'Hopital's theorem here. So we differentiate. This is nothing but limit as x tends to 0 plus of 1 by x divided by negative 1 over x square. Well, I can cancel out one of the x's and the negative x goes to the numerator, and eventually it becomes limit x tending to 0 plus of negative x, which is nothing but 0. So as the value of x approaches 0, the function also takes a value which is very close to 0. So limit x tends to 0 plus of f of x is actually equal to 0. Now this is a very important piece of information which we'll be using when we are solving this question. So let's keep this information aside for some time. Now let's try and find out what is the value of f dash of x. So let's try and find out what is f dash of x. So f of x is x log x plus x. So f dash of x, I'll have to use the product rule, will be x times 1 by x plus log x plus 1. X times 1 by x is 1. So this is going to be nothing but 2 plus log x. So if f dash of x is equal to 0, then that would imply that log x equal to negative 2, or x is nothing but 1 upon e square. So 1 upon e square is a critical point because at this point the derivative becomes 0. This means that this can be a point of local maxima or local minima, or this can be a point of inflection. So let's try and see if it's a point of local maxima or local minima. What is f double dash of x? Well, f double dash of x will be nothing but 1 upon x. So 1 upon x for every value in the domain of x. Remember, domain of x is all positive numbers. So in the domain of x, f double dash of x is always greater than 0. This means that the point x equal to 1 upon e square is a point of local minima. So what is happening to this function? Well, this function is almost going to 0 at the point 0, and we have also seen that this function goes to 0 at x equal to 1 by e, and at x is equal to 1 by e square it attains a minima. So what does this mean? This means that from 0 to 1 by e square, this function goes down. Then from 1 by e square to 1 by e, the function comes up. And then something happens. Let's try and find out what is this something. So f dash of 1 by e square is 0. Let's try and find out the nature, the monotonicity of the function before 1 by e square and after 1 by e square. So from the looks of it, before 1 by e square, this function is a decreasing function, and after that it's an increasing function. So f dash of 1, it's one random value of x in the interval 1 by e square to infinity. In that interval of x, if I take the value of x as 1, you see f dash of 1 is 2, which is greater than 0. This indeed means that the function is increasing after 1 by e square. Well, just for the sake of completion, if you take a point less than 1 by e square, let's say 1 by e cube, at this point you will see that f dash is negative 1, because log of 1 by e cube, that's going to be minus 3, and minus 3 plus 2 is going to be minus 1. So this is less than 1. So this is less than 0. So this is actually coherent to whatever we found out, that the function is decreasing before 1 by e square and is increasing after 1 by e square. So everywhere after 1 by e square, the function is increasing. So this is how the graph of this function will look. From 0, it will decrease till 1 by e square and then increase all the way up till infinity. Why did we do all these things? Because in options 2 and 3, what has been told? So if you take a value of lambda which is 0 to 1 upon e square, then we have to find out the number of solutions this function has. So lambda, notice, is the right hand side of f of x. So f of x is equal to lambda. So lambda is nothing but the output you get when you input any value of x. That's how it is, f of x equal to lambda. So if you put a value of lambda which is positive, what happens? Well, if you put a value of lambda positive, you see that y equal to lambda will intersect this curve at exactly 1 point only. Correct? So exactly at 1 point, y equal to lambda will intersect this curve when lambda is positive. So this means that for a positive lambda, well, 0 to 1 by e square, lambda is positive. For a positive lambda, there is exactly one solution. Correct? Now what happens if you put the value of lambda, which is negative 1 upon e square comma 0? So negative 1 upon e square comma 0, at this point lambda is negative. So what happens when lambda is negative? When lambda is negative, you see there is that small range interval in a domain of x for which the range is going to be negative. In this negative range, for every value of lambda except for when x is equal to 1 upon e square, there are two solutions, correct? There will be two solutions. So when lambda is negative 1 upon e square, when do we get lambda is equal to negative 1 upon e square? It's a difficult equation to solve. So let's plug in the value of x at the critical point. When x is at the critical point, x is equal to 1 upon e square, the value of the function f of x is going to be x log x, 1 upon e square into log of 1 upon e square is going to be minus 2 plus x, which is 1 upon e square. This is going to be minus 1 upon e square. So the value of lambda is minus 1 upon e square at that critical point. So the interval minus 1 upon e square comma 0 for lambda, at every lambda value for this, you will find two y values corresponding. So there are two solutions to the equation when lambda is between negative 1 upon e square and 0. So this is also a correct answer to this question. So let's look at option D now. In option D, we are told that this equation has at least one solution in the domain 1 comma lambda. So in order to do that, let's look at f of x a little more carefully. F of x is x log x plus x, which can be rewritten as x times 1 plus log x. Now in the domain 1 comma lambda, where 1 is a smaller number and lambda is any number greater than 1, what happens to 1 plus log x? When x is a number which is greater than 1, log x is going to be positive. So this quantity is going to be greater than 1. So f of x is going to be greater than x. So f of x will be greater than x for all x in the domain 1 comma lambda. Now look at the graph of the function. So when you put in any value of lambda which is greater than 1 or greater than 0 for that matter, any positive lambda, for any positive lambda we see that the equation has exactly one root, correct? But now what do you see? We see that lambda grows because f of x is nothing but lambda. Lambda grows faster than x, correct? So if you take a value of x and input into this function, you will see that f of x is greater than that value of x, or lambda is greater than that value of x. So if lambda is greater than that value of x, then f of x will definitely have one root in 1 comma lambda. So this is how you are going to analyze this. Since lambda is always greater than x, lambda grows faster than x. So if you input a value of x between 1 and lambda, the value of f of x will be greater than that x, and hence f of x equal to lambda will definitely have one solution in the interval 1 comma lambda. So in this way we see that the last option is also a correct answer to this question. This means that options B, C and D are all correct answers to this multiple correct answer kind of question. It's a question which involves extreme amount of analysis and a lot of applications of derivatives. So you need to analyze this question very well in order to solve this question. A very beautifully crafted question, and I hope you had fun like me in solving this particular question. Now in this next question, we've been told that f dash of sine theta is negative. Also, f double dash of sine theta is positive. Now this is valid for all values of theta which lie between 0 and 90 degrees or 0 and pi by 2 radians. Now another function g has been defined. G of theta is nothing but f of sine theta plus f of cos theta. The objective of this function is to find out the monotonicity of g of theta in two intervals, 0 comma pi by 4 and pi by 4 comma pi by 2. Now this is also a multiple correct answer kind of question. So as soon as you look at the options, you will understand that options 1 and 3 contradict each other, options 2 and 4 contradict each other, which means either of 1 or 3 is correct, either of 2 or 4 is correct, both of them cannot be correct. So let's get into this question. Let's try and solve this question in a very systematic way. First of all, what is g dash of theta? Because we need to find out the monotonicity of g. Let's try and find out what is g dash of theta. Now g dash of theta is nothing but f dash of sine theta, and then I need to use chain rule of differentiation, which will give me a cos theta, plus f dash of cos theta into negative sine theta, which is because of the chain rule. So I'm going to write a minus here, minus f dash of cos theta into sine theta. So this is g dash of theta. So nothing can be found out about this because we have no idea about what is f dash of cos theta. there is some information about f dash of sine theta, but none whatsoever about f dash of cos theta. So let's try and see if we can gather any information about f dash of cos theta. So let's go back to the problem statement. They've told f dash of sine theta is negative, f double dash of sine theta is positive. So can we infer something based on this? Is what is the objective that is there in my hand now. So I'm going to call sine theta as some other variable x. Okay, so this means that f dash of x is less than 0. But remember, theta runs from 0 to pi by 2, which means sine theta runs from 0 to 1. This is for all x in the interval 0 to 1. Now this is going to help me a little, because what will happen to cos theta when theta is between 0 and pi by 2? When theta is between 0 and pi by 2, cos theta is also going to be between 1 and 0, or in other words 0 and 1. So it is going to behave exactly like how f dash of sine theta behaves. So since we have a relation for f dash of x being less than 0 for all x running from 0 to 1, f dash of cos theta will also be negative, because when theta is in the interval 0 to pi by 2, cos theta is going to be between 0 and 1. In fact, it's going to be between 1 and 0, which is exactly like 0 and 1. And we know what happens to f dash of x when x is between 0 and 1. It's going to be negative. So we've got one interesting piece of information already. But that's not enough. We need more information. See, if f dash of x is less than 0 for x between 0 and 1, this means function f is decreasing in 0, 1. Correct? And also f double dash of x is greater than 0 for all x in 0 to 1. Because of the same logic, this means that f dash is increasing in 0, 1. Now these pieces of information are going to be very vital in our analysis, because now this question is going to be completely analysis question. So now g dash of theta is this value, and I know what happens to f dash. I know what is f dash of sine theta. F dash of sine theta is less than 0. F dash of cos theta is also less than 0. F is increasing, in fact decreasing in 0, 1, and f dash is increasing in 0, 1. I'm going to make use of all these pieces of information. So in the interval 0, pi by 4, that's the first interval of interest for me. What is the case? In this interval, cos theta is greater than sine theta, correct? So cos theta is greater than sine theta, and then what? Because f dash is an increasing function and cos theta is greater than sine theta, f dash of cos theta will also be greater than f dash of sine theta, right? Because f dash is an increasing function. So f dash of cos theta is going to be greater than f dash of sine theta, simply because in this interval cos theta is greater than sine theta, right? Now let's look at the nature. F dash, however, is less than 0 in this interval, because f dash is less than 0 for x between 0 and 1, and cos and sine theta are always between 0 and 1. So this means that f dash of cos theta is a smaller negative number and f dash of sine theta is a larger negative number. Because f dash of sine theta has to be less than f dash of cos theta, f dash of sine theta is a larger negative number, right? Now go back to the expression of g dash of theta. F dash of sine theta is a larger negative number and cos theta is a larger number in this interval. F dash of cos theta is a smaller negative number and sine theta is a smaller number. So you have a large number multiplying a larger negative number. So the net quantity is going to be a large negative number. From that you are subtracting the multiplication of a smaller negative number with a small number. So you are subtracting a smaller negative number from a larger negative number. So if you subtract a smaller negative number from a larger negative number, effectively you are going to get a negative number. It's like you're subtracting -3 from -5. So -5 minus -3 is going to be -2, a negative number. So effectively you are getting a negative number. So this means that in the interval 0, pi by 4, g dash of theta is going to be negative, or in other words, g is going to be decreasing in this interval. A very beautiful analysis. Now you know the drill. I don't even need to help you in finding out what happens in the next interval, because in pi by 4, pi by 2, sine theta is greater than cos theta, and because f dash is an increasing function, f dash of sine theta is greater than f dash of cos theta. And we also know that f dash is always less than 0 in this interval. So this means that f dash of sine theta is a smaller negative number and f dash of cos theta is a larger negative number. So then what is happening? You have a small negative number and you have a small positive number. From that you are subtracting the product of a large negative number and a larger number. So what is happening? You have a smaller negative number and from that you are subtracting a larger negative number. It's like -3 minus -5, for which you get a positive number. So g dash of theta is positive in this interval pi by 4, pi by 2, or g is increasing in this interval. A very beautiful question, a lot of analysis to be done, very little derivatives as such, but it's all about analyzing, and we arrived at the solution. G is decreasing in 0 to pi by 4 and increasing in pi by 4 to pi by 2. A very beautiful question, and I had a lot of fun, and I hope you too had a lot of fun solving this question. Now here's another question. This is also a very interesting question. Let's have a look at this question. In this question, we've been given f of x, which is nothing but the maximum of yet another function, y square minus 2xy plus 1. And y can take values between 0 and 2. The objective of this question is to find out the minimum value that f of x can take for all real numbers x. So first of all, let's try and analyze what happens to this function here. Okay, I'm going to call it g of y. G of y is nothing but y square minus 2xy plus 1. This is my function g of y. Now, for any particular value of x, g is still going to take infinite values because y can lie between 0 and 2. Since y can lie between 0 and 2 for every particular values of x, there are infinite possibilities for g of y. So g of y will behave like an independent function of x for every value of x. For a particular value of x, g of y will be independent of x. So this is an important piece of information that we will use in this question. I'm going to find out what is g dash of y. G dash of y is going to be 2y minus 2x because x is going to act like a constant. So this, now I'm going to evaluate this to 0. When I evaluate g dash of y to 0, I get the value y equal to x. Why did I find out the derivative of y? Because f of x is the maximum value that this function can take, isn't it? The definition of f of x is the maximum value that g of y can take. Now, where will a maximum occur? Well, maximas will occur at critical points or at the endpoints. So we have found out the critical point of this function. There's only one critical point, which is going to be y equal to x. That's going to be the point where a function can attain a maximum value, or else the function will attain maximum value at the two endpoints, 0 and 2. So what is g of 0? G of 0 is going to be nothing but 1. G of 2, if you plug in the value of 2 here, you get 4 minus 4x plus 1. That's going to be 5 minus 4x. And what is g of x? X is the critical point. When y equal to x, you get x square minus 2x square plus 1, which will be nothing but 1 minus x square. So my function f of x is going to be the maximum value of these three functions: 1, 5 minus 4x and 1 minus x square. Now analyze again. 1 and 1 minus x square. For every value of x other than 0, 1 is going to be greater than 1 minus x square. Look at the graph of 1 and look at the graph of 1 minus x square. 1 is always going to lie above 1 minus x square. They meet at the point x equal to 0. So the maximum of 1 and 1 minus x square is always going to be 1. What happens to 5 minus 4x? So we have to now find out the maximum of 1 and 5 minus 4x. Now 5 minus 4x is a linear graph. So if you plot the graph of 5 minus 4x, you will see that 5 minus 4x cuts the line y equal to 1 at exactly one point. That is when x equal to 1, correct? So every value of x greater than 1, the value of 5 minus 4x is going to be less than 1, and every value of x less than 1, the value of 5 minus 4x is going to be greater than 1. So the definition of f of x is now going to be 1 when x is greater than or equal to 1, or 5 minus 4x when x is less than 1. A very beautifully constructed question, correct? So now let's draw the graph of f of x. So the graph of f of x is going to be 5 minus 4x all the way from negative infinity till x equal to 1, and after x equal to 1 it's going to have the constant value of 1. The objective was to find out the minimum value of f of x, and the minimum value of f of x is nothing but 1. A very beautiful question. It required you to understand the nuances of differentiation really well, and again a question which was very high on analysis. I hope again you had fun solving this question. We will solve 2 more questions in this session, and then of course close this session. Now here is yet another very interesting question. In this question, we've been told that f of x is x square plus 3 divided by the greatest integer of x plus 1, and x is between 0 and 2. The objective of this question is to find out the maximum value of f and the minimum value of f and add them. We have to find out what is f max plus f min. Now, to a lot of you, this might seem like a differentiation question because you have to find the maximum value, the minimum value. So the routine procedure is to find out the derivatives, the second derivatives, find the point of local maxima, local minima, evaluate the value of the function there, and arrive at the solution. Well, that's going to be a very, very tedious process. So we are going to completely avoid that and do this question using graphs of functions. Absolutely no differentiation here, even though this looks like an application of derivatives questions. So I'm going to now rewrite the definition of the functions because there is a greatest integer of a function. So this greatest integer function is going to cause us a lot of trouble. So I'm going to divide my domain. So I'm going to say that x lies between 0 and 1 is my first subdomain. So what happens when x lies between 0 and 1, and I am going to consider the domain where 1 is not included. 0 is included but 1 is not included. So what happens to x plus 1? When x is 0, greatest integer of 1 is going to be 1, and when x is 1, the greatest integer of 2 is going to be 2. So any value slightly less than 1, which is in this subdomain, the value of greatest integer of x plus 1 is going to be 1. So the definition of function in this subdomain is going to be x square plus 3 divided by 1. I'm going to just do away with the 1. It's just going to be x square plus 3. Now what happens between 1 and 2? Again, I'm not going to include 2. At 1, the value of that greatest integer of x plus 1 is going to be 2. And as the value of x approaches 2, in fact when it becomes 2, it is going to be the greatest integer of 3, that's 3. Slightly less than 2, the value of greatest integer of x plus 1 is going to be 2. So the definition of the function is x square plus 3 divided by 2. And of course when x equal to 2, you have the definition x square plus 3 divided by 3. Now, you can differentiate these functions in different intervals, find out local maxima if it exists, local minima if it exists, evaluate the value of the functions at the end points and see what happens. That's a very cumbersome way of solving this question, believe me. So I'm not going to use that. Let's try and plot this. X square, we know what happens to x square. X square is a quadratic function. That's going to be an upward parabola. X square plus 3, I'm just going to shift it above by 3 units. So when x is equal to 0, x square plus 3 will have a value of 3. And when x equal to 1, this will have a value of 4, correct? Now, what happens when you take the other function, x square plus 3 divided by 2? At the lower interval of 1, the value of the function is going to be 4 by 2, which is equal to 2. See, so this value is even lower than 3. And at the other end point, the value of the function is going to be 4 plus 3, 7 divided by 2. And when x equal to 2, the value of the function is going to be 7 by 3. So these are all increasing functions. They are strictly increasing functions in their subdomains, but the functions are not continuous at points 1 and 2. These are strictly increasing functions. So the maximum value in a particular subdomain will occur at its end point. The minimum value will also occur at its lower end point in each subdomain. So that's what I have evaluated, and I find out that the value of f max is equal to 4 and the value of f min equal to 2. So the answer to this question is 4 plus 2, which is 6. So the correct answer to this question is 6. Well, we just needed to use a little bit of idea of differentiation. What is a monotonically increasing function? That's all. Nothing else from differentiation was really needed to solve this question. It was all about visualizing, and we arrived at the solution very quickly. Now, the next question that we'll be solving will be a question that will test your understanding of extremas. So these are questions where you have to maximize or minimize things. Remember that there are plenty of good examples at the back of your NCERT textbook. Solving them will give you a very good idea of how extrema questions are, and mostly they do not twist extrema questions a lot beyond how the questions appear in the NCERT textbook. So in order to give you a small flavor of how these extrema questions are, let's solve one extrema question. So in this question, the problem statement is quite lengthy. So let's visualize the problem statement. There is an island, there is a shore. The shortest distance of the island from the shore is 5 kilometers. So that point on the shore, which is at the shortest distance from the island, I'm going to call that point A. A swimmer starts swimming from the island, and he starts swimming from the shortest distance away from the shore, and he starts swimming and he has to go to his house. Now, how far is his house? His house is 11 kilometers along the shore away from that point A, which is the shortest distance from the island. So now we have to find out the point where he has to land on the shore after swimming, so that the time that he takes between the island and the shore is minimum. There is a little more information. Of course, we need to know what is his speed. He has different speeds on water and land. He swims at a speed of 2 kilometers per hour and walks at a speed of 3 kilometers per hour. So based on all these things, we have to optimize the amount of swimming he does and the amount of walking he does so that he reaches his home fastest from the island. So first of all, let's look at this triangle that is formed. There is that shortest distance of 5 kilometers between the island and the point A. I'm going to call the point on the island as S. That's where our swimmer starts swimming. So SA is going to be 5. H, which is the point that is where his house is, that's at a distance of 11 kilometers from point A. And there is another point that is going to be my point X. That's my variable point. That is the point where the swimmer swims to from the island. Now the distance AX is going to be called small x. So the distance XH is going to be 11 minus x. So the distance that he's traveled in the sea, that can be found out using the Pythagoras theorem. So the distance traveled in the sea, that's going to be under root of 5 square plus x square. And the distance that is covered on land, that is going to be equal to 11 minus x. Now the time taken on the sea is going to be distance divided by speed. So that is going to be 25 plus x square all under root divided by 2. And the time taken on land will be 11 minus x divided by 3, because that's the speed on land. So the total time taken will be under root of 25 plus x square divided by 2 plus 11 minus x divided by 3. Now we need to minimize this term, which means I will take the derivative of t with respect to x and equate it to 0, which gives me 1 by 2 into, of course, 1 by 2 times under root of 25 plus x square. Do not forget to remember the chain rule of differentiation. That gives me a 2x plus, of course, 11 is constant, so that gives me a minus 1 upon 3. Now all this is equal to 0. You take a you cross multiply to take a least common multiple, and you will find out that this is going to be nothing but, well, the 2's cancel out, so this is going to be nothing but 3x minus 2 times under root of 25 plus x square equal to 0. I take the root of 25 plus x square with the 2 onto the other side and square it to get 9x square is 4 times 25 plus x square, or I get 5x square to be equal to 4 times 25, and upon simplifying I get x equal to 2 times under root of 5. Of course, negative x does not make any sense, so I say x is equal to 2 times under root of 5. So I consider the value of x is equal to 2 times under root of 5. So when x is equal to 2 times under root of 5, so that is at a distance of 2 under root of 5 kilometers away from point A, if our man swims to this point, then the time that he's going to take is going to be minimum to reach his house. So this is a general trend that you always follow when you have an extrema question. You first identify the variable that you need to maximize or minimize, differentiate it and put that equal to 0. In order to determine whether it's a point of local maxima or local minima, you take a second derivative. Now look at my first derivative. My first derivative is x divided by 2 times the under root of 25 plus x square minus 1 by 3, that's a constant. If you take a second derivative of this, now if you take a second derivative of this and then you input values of x, which is 2 root 5, you will see that that point is actually a minima, because the second derivative of t will be positive for 2 root 5, so you will get a point of local minima itself. So this is how you solve extrema questions. Not many varieties are there in this particular section of the chapter, so solve enough number of problems from here to get enough practice to solve extrema questions. Applications of derivatives is a massive chapter, and that is why we have covered this chapter in 2 different sessions. I hope you had a lot of fun understanding the concepts and seeing the different varieties of questions that are possible from this chapter in your JEE examinations. Prepare very well from applications of derivatives because it's an important chapter. Questions inevitably come from here. Make sure you do not lose marks in the questions that come from this chapter. If you like this video, please subscribe to our channel, because we are going to make many more such videos, and every time a video comes, you will be notified about it. I hope you had a lot of fun in this session, and I will see you very soon with yet another chapter and lots of questions and lots of fun in our preparations for the JEE examination.
For more videos and live lectures on the JEE, click on the subscribe button now.